طيب بسم الله الرحمن الرحيم. So last time we talked about some phenomena or some performance measures that we can use in order to evaluate the performance of the line encoding schemes. And we have discussed first the baud rate or the signal rate, and we have discussed how to calculate the minimum bandwidth required for any digital signal. And then we discussed three important phenomena, including the DC components, the baseline wandering, and the what was the third one? Self-synchronization. Okay, so today we are going to discuss the line encoding schemes, and the line encoding schemes are classified into 5 categories. Each of these categories has one or more of these line encoding schemes. So quickly, the first one, or the unipolar. The unipolar actually talks about that when the signal levels are, all of them are 0 or above. Okay, so unipolar talks about all the signal levels when all the signal levels are 0 or above. Polar talks about the fact that the signal levels are either above 0 or below 0. Okay, above 0 or below 0. But there's no signal level of 0, which is, we'll see some exception to this, but there's no actual signal levels that it's used to map the digital numbers. Bipolar talks about using more than 2 levels. We can use above 0, one level, 0 as another level, and below 0 as a third level. So we have at least 3 different signal levels to represent the digital signal or the digital data. And then we'll talk about the general case of multi-levels if we have more than 3 levels or above. So we can talk about the general case that we have multiple levels to map the digital data. And then we talk about the multi-transition. So instead of having multiple levels, we will use 3 levels, similar to bipolar, but here we'll talk about multi ways of transitioning from one signal level to another. So we'll talk about the logic that we use to make this transition. So the simplest form of line coding is actually the unipolar non-return-to-zero. For that one, we have only 2 levels, and it's the simplest. We have simply the positive voltage to represent the 1, the 0 voltage to represent 0, and that's it. Okay? So for each of these line schemes, let's try to analyze the performance of this line coding scheme based on all the things that we have discussed before. So first of all, we know that this is the simplest, so it's very simple. It requires only 2 signal levels. One of them is 0, so it's easy to generate. So this is the advantage. The disadvantages are a lot. Okay, one of them is the fact that if I have repeated 1s or repeated 0s, what will happen? If I have all 1s, what will happen? I will have straight signal of positive voltage. Okay? If I have consecutive 0s, I will have a straight signal of 0. Okay? So what is the implication of this? The implication of this is actually enormous. Because on one hand, if I have positive voltage, constant positive voltage from 0 all the way, This means that I have high average power, okay? I have high average power, which means that because this is constant, this means that the frequency of this constant signal is 0, which means that I have high average power in low frequency component, which is what we refer to as a DC component. Okay? So for either the case of consecutive ones or consecutive zeros, we have a serious issue which is related to the fact that we will have signal power in low frequency components, which is the DC component that we talked about before. So also, if I have consecutive ones, this means that I will also have the other phenomenon that we talked about, which is baseline wandering. Why? Because if there is no change, then the baseline will start to grow based on the fact that I have repeated positive voltage. So the baseline will start to increase gradually. Okay? So it will go high, and then if I have consecutive zeros, it will start going low gradually and steadily. So I have baseline wandering, I have DC components, and also I have no self-synchronization. Why? Because if I have constant voltage with no change, then there is no timing information, right? And we talked about one example where we can make a change in the middle of the bit to add some timing information which allows the receiver to resynchronize itself. Okay? But this one does not have any timing information. Timing information basically happens if I have a change in the middle of the bit. Some change which tells the receiver that pay attention to the fact that this is the middle of the bit. So if there is any missynchronization in the clock at the receiver side, it resynchronizes itself from the signal itself while it's receiving the signal itself. But this scheme does not have this feature. It does not have any timing information, at least when I have consecutive ones or consecutive zeros. Okay, so I have high average power. I have DC components because if the signal is constant, I have zero frequency and positive voltage, which means that I have high power in the low frequency components, which is, as we said before, this is bad for special types of channels that does not really pass the low frequency components efficiently. And we have talked about examples like wireless, like any channels that is very inefficient for transmitting the low frequency components of the signal. Okay, and also the self-synchronization. This normalized power is based on the fact that on the average I will have ones. For ones I have positive voltage, and for zero I have zero. So if I have zero, I don't have any voltage, in which case the power is zero. But if I have positive voltage, which happens 50% of the time, therefore I have the factor or the weight half here. So if I have this half, so half multiplied by V squared, which is the positive voltage, plus in the case of zeros, which I have it 50% of the time, the power is zero. So the normalized power or the average power is around V squared over 2. And if I were to draw the, I hope this, okay. And if I were to draw the frequency spectrum, then we will find it something like this. So it will look like this. Okay, I have actually high power components in the zero frequency, okay, and then it decays as the frequency goes higher. Okay, so we'll see this curve repeated in later line coding schemes. So it seems that this coding scheme has all the disadvantages. The only advantage is that it's simple to generate because it has only one or two signal levels. One of them is 0. So it's very easy to generate. Okay? Type. Second, line coding scheme tries to actually, the motivation for this is that we try to, because for the other one, the average voltage is always above 0, right? Because the other signal level is 0. So if I have ones, the average voltage is high. So the average power tends to be high in that case. Here, one thing that this scheme tries to resolve is the case of the average voltage. Because if the average voltage is low, this means the average power in general is low. And it does that by using the polar level as opposed to unipolar. By polar level here, we mean that we use two levels. One is above 0 and the other one is below 0. So the simplest way is to map 0 to positive voltage and 1 to negative voltage. All the other way around. It doesn't matter. So if I do that, simply, I will try to reduce the average voltage, hence reduce the average power. So that's the only thing that the only added advantage here. But is there any other advantage? Let's see. First, for the previous one and this one, the baud rate is how much? The baud rate, as we have talked about before, the baud rate is simply S equals C, the case factor, multiplied by N multiplied by 1 over R. What's R here? R is the ratio between the data element and the number of signal elements that represent this data element. What is R here? 1. So I have one data element corresponding to one signal element. So R is 1. Okay? So if I have N, any bit rate, then the baud rate is N multiplied by 1 multiplied by the case factor. Here, the case factor, as we discussed yesterday or in the previous lecture, refers to the average baud rate. Because we have two extremes, right? One extreme, if I have at every bit level, I have one change. So this is the maximum, or this is the worst case. And the other extreme case is when I have no changes at all. So C is usually somewhere between 0 and 1. And we usually select it as half, or 1 over 2. So that's why the average baud rate is around N over 2, as it shows here. So the baud rate is N over 2, which simply is equivalent to, again, the minimum bandwidth. The minimum bandwidth that I need in order to transfer this digital signal. So the minimum bandwidth is somewhere here. The minimum bandwidth is at this point here. Okay. So this is the minimum bandwidth I need in the channel in order to transfer this digital signal. And still, this uses some approximation. So if I want more accuracy or more better performance for transmitting this digital signal, I need to increase the bandwidth more than the minimum bandwidth. But the minimum bandwidth I need equals to the baud rate, and the baud rate here is N over 2. Okay? This is no change from the previous one. The previous one still has R of 1, صح? and C equals 1/2. So again, the bandwidth or the baud rate or the minimum bandwidth is still N/2. Okay, so the only advantage added here is that the average voltage here tends to be around 0 or very minimal compared to the previous one, because one of the levels in the previous one is 0. So the average voltage tends to be always positive, which increases the average power. Okay? So let's see, did this one solve any problem related to baseline wandering? The answer is no. Especially for the scheme which is the scheme above here. The scheme above here, there is a slight change between this one and this one. And the one underneath. Okay, so we'll talk about that. So assuming that we have the one above here, the one above here still suffers from the consecutive 1 problem and consecutive 0. Because if there is consecutive 1s, I will always have constant voltage positive. If there is consecutive 0, I will always have constant voltage negative, or the other way around. Which means that I still have a DC component, and the DC component is actually, it's very clear from here. DC component talks about the fact that you have high power component in the 0 frequency, or in the low frequency component, in the low frequency values, right? So this is what we refer to as DC component, which is apparent from the fact that if I have consecutive 1s or consecutive 0s, I have constant voltage positive. So I have basically high power component in the low frequency. Okay, so baseline. How about baseline wandering? Well, still the problem is still there, because again, if I have constant voltage, then I will have the baseline still goes up continuously or goes down continuously. So I have baseline wandering. Okay. How about self-synchronization? Nothing has changed, because again, if I have constant voltage, I don't have any change in the middle of the bit, so I don't have any timing information to tell the receiver where to stop at the bit boundary. So again, I don't have any self-synchronization. Okay. The only difference that this the lower scheme tries to do is that it says, instead of mapping one-to-one the bit to a signal level, what I'm going to do is that I will use the bit information to do some kind of polarity change, either to change the signal level or to remain constant. Okay, so here what I'm going to do is that if there is so forget about the first bit level positive. If there is 1, I'm going to change the signal level. If there is 0, I'm going to keep the signal level as is. That's what this scheme does. So it's changing the signal level by inversion. It's like toggling. Okay, so this one here does not depend on the previous bit at all, right? So the upper one does not actually take into consideration what signal level I have now. If the incoming bit is 0, then I map it to a specific signal level. If the incoming bit is 1, then I have it to another signal level, and that's it. The other one uses the toggling. So if I have 1, I will toggle. If I have 0, I will keep it as is. Okay. So does that actually fix any issue? Let's see. So this one underneath here, if I have consecutive zeros, right, then this means no change, صح? Which means constant. So in that case, I will have constant voltage, similar to the one above, and nothing changed, right? So nothing is resolved here. But what if I have consecutive ones? Yes. if I have consecutive ones, then if this level is positive, then I have if this is like 1 مش عارف انا البتاع ايوه كده 1 1 1 1 and so on. So the first one is positive, then I have 1. What does it mean? I have to toggle, which means I have to go down. And then if I have 1, which means toggle, so I have to go up. And then 1, which means toggle, go down. So I will keep going up and down. Okay? So I will not have the constant voltage. So at least I resolve the issue of self-synchronization and baseline wandering only for the case of consecutive ones. Only. For the case of consecutive zeros, I still have the same problem. But at least I fixed it in 50% of the cases. I fixed it in 50% of the cases. Remember, still I have DC component. Why? Because if I have consecutive zeros, okay? If I have consecutive zeros, then again I have zero frequency, I have constant voltage, and the power is positive. صح? In that case, as you can see here, I still have high power values in the zero frequency component. Okay? And that happens because if I have consecutive zeros, I still have power, high power, at zero frequency. Okay? For the two cases. يعني what this scheme tries to do, the lower scheme, what it tries to do is that it tries to solve 50% of the problem if I have consecutive ones by using the concept of a toggling. So by toggling, at least I was able to fix 2 of the 3 problems for this particular case of the consecutive ones. 2 problems are I fixed the DC component, the baseline wandering, and I fixed the self-synchronization because I have some changes. Okay. So this the change between the non-return to zero level and the non-return to zero inversion is actually minimal. Again, the simplicity here is that I still have two voltage levels only. Okay, I have only two voltage levels only. So the overhead is low when it comes to generating this digital signal. So the next scheme tries to resolve the issue of first the DC component and the self-synchronization. Drastically. It tries to drastically resolve the issue of DC component and the issue of self-synchronization. And what I can do here is that I can use the zero voltage level as a third level, as another extra level, to help me to add some timing information and changes in the middle of the bit. Okay? So by having a change in the middle of the bit, this means that in every single bit I have to return to zero. That's why it's called a polar return to zero. So in every bit I have to use half the duration to use a specific signal level, and the other half I have to return to zero. The fact that I have to return to zero in every single bit is very useful in many cases, and it has some disadvantage. Okay. The advantages is that I inherently added some timing information, right? So this change will help the receiver recognize that this is the middle of the bit. So the receiver now will rely on one extra piece of information in addition to its own clock. So if it relies only on its own clock, then there might be some clock drift which will affect the performance, as we have discussed last time. So here, it says, okay, I will rely on the clock, but I have another piece of information, which is a change in the incoming digital data. So I will use that for my benefit, and I will try to resynchronize myself if I lose synchronization. By doing this, let's see, by doing this, we always have a change even if we have consecutive ones or consecutive zeros. صح? Right? So we always have change in frequency. So even if you have consecutive ones or consecutive zeros, you no longer have constant voltage. صح? Which means I have no zero frequency. There's no case whatsoever that you can find here that has zero frequency. Zero frequency coming from a constant voltage. There's no such thing here. Which means I have no power whatsoever in the zero frequency component. So there is no DC component here. So the issue of DC component is not here. Okay? So the issue of self-synchronization has been resolved. The issue of DC component has been resolved completely. Okay? What about baseline wandering? Well, you can argue it's not actually resolved. It's not resolved completely. Why? Because if I still have consecutive ones, I always have positive voltage, right? I always have positive voltage. Or zero. So the baseline will keep increasing and then keep constant, and then increasing and then constant, and so on. Because if I have consecutive ones or consecutive zeros, the voltage is always positive, and if I have consecutive zeros, the voltage is always negative. So again, the baseline one is not resolved completely, but at least I was able to resolve DC component. I was able to resolve the issue of self-synchronization. Type. What is the disadvantage? The disadvantage here is that I doubled R, صح? Because I'm using two signal elements to map or to represent one data element, صح? So R is doubled معناها ايه؟ The baud rate is doubled معناها ايه؟ The bandwidth is doubled, صح? So that's why we have the baud rate equals to N, not N over 2. So the baud rate is doubled, and the bandwidth is doubled. So it's like, by doing this, it's like I shifted the digital signal spectrum in the frequency away from zero. But by doing that, I actually double the bandwidth. So the overhead here is that I double the bandwidth in order to resolve the DC component and self-synchronization. And the baseline wandering is still there. It's not as major as it was before, because at least half of the bit is zero. So the increase is not going to be that major, but still there. Okay? So this scheme talks about the fact that I'm using zeros for the zero signal level for my benefit to always return to zero. By doing that, I created some change which helps me resolve the DC component and self-synchronization. So this is called polar return to zero scheme. Okay. Of course, in the return to zero scheme, I have 3 signal levels. صح? I have 3 signal levels. So I had to add another signal level, which, by the way, is not used to map the data itself. The zero is just added to inherently create some timing information and create some change in the digital data, in the digital signal. which eliminates the power in the zero frequency component. But still I have 3 signal levels. 3 signal levels معناها more complicated. It's more complicated in terms of data signal generation, it's more complicated. So this polar biphase, the other one is polar because the 0 is actually not used for data representation. It's actually used in the digital signal just to create some timing information. This is polar biphase. This one tries to resolve this extra signal level. So it will have the exact same benefits like the return to 0 with only 2 signal levels instead of 3. Okay? So I did not resolve the bandwidth issue here. So the bandwidth issue is still the same. So the bandwidth is still the same because again, I have, what I'm trying to do here is that 0 is always created using 2 signal elements. One is above 0 and the other one is below 0. And 1 is again created in the same signal level but inverted. Which means you are actually using the same signal, the same digital signal, and you are inverting the phase of this signal for the case of 1. So for the case of 0, the signal goes from positive and then negative. For the case of 1, it goes from negative and then positive. So it's the same signal, but the phase is 180 degrees. That's why it's called biphase. So you are using the same digital signal and you are inverting the phase of this signal. So for 0, you are using 0 phase shift. For 1, you are using 180 degrees. Okay? So by doing that, did I lose the timing information? No, because it's still there, right? So I still have some change in the middle of the data. In the middle of each bit, I still have drastic change, which tells the receiver when to stop at the bit boundary. So, how about, so the self-synchronization is there. Baseline wandering is actually even much better here. It's much better here. Better than the return to 0 scheme. Why? Because even if you have consecutive zeros, the baseline will always go up and go down, go up and go down, and always around the 0. So, because it goes up and goes down, it will always be close to 0, which is what I need. So I need the baseline to be around 0 all the time. And that's what will happen here. So baseline wandering is much better than before. But how about DC component? Well, DC component as well is resolved, صح? Because even if I have consecutive zeros or consecutive ones, I have no 0 frequency خالص, صح? I always have a change. So this resolved the 3 components and actually resolved the issue of 3 signal levels. So this is even simpler. So this is simpler. However, I was not able to resolve the issue of bandwidth. So the bandwidth here is still doubled. I mean, compared to the previous schemes. So here, the advantage is that I eliminated 1 level of the 3 levels, so I have only 2. And by changing the phase, actually this is a very smart and simple idea. So baseline wandering is not there, DC component is not there, self-synchronization is there, is good, okay? But the only problem here is the bandwidth. And that's why this is actually used a lot in Ethernet. This is used in Ethernet a lot. This is used as part of the physical layer in Ethernet. As you can see, it's a very simple line encoding scheme, not complicated, using only 2 signal levels. And by changing the phase, I was able to inherently create some timing information, create change in the middle of the bit in all the time, even if I have consecutive ones or consecutive zeros, which means that no DC component and the self-synchronization is there. And that's why it's actually named after Manchester, who is the inventor of that. It's called Manchester. Okay? So the next natural thing is to take that and think about some way to enhance the bandwidth a little bit. It seems that we have gone through many levels of improvement, but still the bandwidth seems to be an issue. The bandwidth seems to be an issue. So the next scheme tries to resolve this issue of bandwidth. So as you can see in the spectrum here, I still have no DC component and the bandwidth is shrinking. So let's see how does this happen. So the bandwidth here is shrinking. So we have gone back to n/2, which seems to be very good. Okay. So what this tries to do is that it uses 3 values. So again, I have to have some overhead. So I was able to reduce the bandwidth, but I have to increase the number of signal levels. So that's the cost. The cost here is that I'm using now 3 signal levels. But here I'm using the 3rd signal level not to return to 0 to create a change. No, I'm using it as part of representing the digital data. Let's see how. So we're using 3 values. The voltage level of one data element is at 0, while the voltage level of the other element alternates between positive and negative. What does that mean? This means that if I have 0, then I create constant voltage of 0. If I have 1, then what I'm going to do is that I'm going to toggle the signal level from positive to negative. So the first one here is positive, and then the next one is negative, and then the next one will be positive, and so on. So 0 is constant, while 1 is you are always toggling from positive to negative. Right. It seems that we have gone back to the same problem of constant voltage. So someone might argue that here I have DC component because I have constant voltage. So how come now I have in the spectrum here, I have no power at the 0 frequency? How does this happen? Because if I have 0, 0, 0, 0, if I have consecutive zeros, this means that simply I will have constant voltage of 0. صح? But what is the power in that case? What is the voltage level? 0, which means that the power is 0. صح? طيب, if I have consecutive ones, what is the average voltage? Do I have any 0 frequency in that case? Because if I have consecutive ones, I have positive, negative, positive, negative, positive, negative. So I have no 0 frequency. صح? طيب, يبقى in consecutive 1 case, I have no 0 frequency. In consecutive 0, I have 0 frequency, but the power is 0 because the voltage level is 0. So that's why in all cases, you will find that the power at the low frequency component is always zero. Is always zero. You have no such component, you have no such case that you have a continuous voltage level above zero. You will never have. You have no such thing. Okay? So remember that we have gone back to R equal 1 here, right? Because we are using one signal element to map one data element, right? Unlike biphase, biphase uses two signal elements. So R is equal to 1 over 2. That's why that was the original problem that caused the bandwidth or caused the baud rate to be doubled. But here, we have gone back to the same unity value for R, right? So the benefit here is that the bandwidth is n over 2 because R is 1. And of course, the C factor is 1 over 2. That's why I have n over 2. So the bandwidth was is shrinking now. It's 1/2. And I have no DC components. Okay? I lost the timing information only in the case of a consecutive zeros. Yes. So that's another drawback here. So I cannot say that this one is much better than Manchester or Manchester is better because each one has goods and bads. So the Manchester one does not have any, it does not have a DC component, does not have baseline wandering, and it has self-synchronization. This one loses the timing information or loses the self-synchronization only for the case of consecutive zeros. For the case of consecutive ones, I still have change, up and down, goes up and down. So I don't have this problem. And the good thing here is the bandwidth, or the baud rate. The baud rate is 1/2. The pseudo-ternary here is just the complement of this. It's simply the complement of this. So this uses the 0 to toggle the level, and the 1 is always 0. So it's actually the exact same complement of this. So the pseudo-ternary is the complement. It's not like inversion like the one before. So this is just the complement. It does not have any added value. So it's just two variations of the same technique. One uses the digital data 1 to toggle the signal level, while 0 is 0 voltage. The other one uses the 0 to toggle, while uses 1 as a 0 voltage. So it doesn't matter. So there's no added value for here. It's just the toggle. Actually, I don't see why they add it in the book. I don't see the point. Okay, so that's so this is all the cases where we have two signal levels that are used to 2 or 3 signal levels, if the 0 signal level is included, to represent the digital data one single bit at a time. One single bit at a time, right? The multi-level techniques talks about the fact that we will actually group the digital data into small groups of more than 1 bit. And then we can use the different signal levels, okay, to map to a group of bits. And the way that this happens is really simple. So we have, let's say that this group of bits, we are going to use مثلا 2 bits at a time. If I have 2 bits at a time, this means I have how many combinations? 4 برافو عليك اللي هي ايه 2 to the power 2 2 to the power the group size. So if I have 3 bits, this means I have how many combinations? 8. If I have 4 bits, then I have 16. صح؟ اللي هي زي الاي بي ادرس زي ما كنا بنعمل في 455. صح؟ Why? Because I always start from 0 0 all the way to 1 1. صح؟ So I have a number of combinations equals to 2 to the power the group size. So somehow for each of these different combinations, I need to have unique representation of the signal elements. I need to have unique signal elements to represent these different combinations. Right? So what I'm going to do is that either I will keep the number of signal elements as 1 and I change the level, I use different levels. صح? That's 1 degrees of freedom. That's 1 of the degrees of freedom. I can have 1 signal element and different levels. So for example, if I have groups of 2 bits and I have 1 signal element, this means I need to have how many signal levels? 4. And if I have 3 bits, then I need to have 8 signal levels. So that's 1 degree of freedom. What is the other degree of freedom? I can use more than 1 signal element. So I can have more than 1 signal element. In which case, how many signal levels I can generate? Many. So the number of this is actually the number of signal levels to the power of the number of signal elements. And if you do the whole combination, then it's simply اللي هي دي. L to the power n, where L here refers to the number of levels you have in each signal element, and n refers to how many signal elements you are using. Okay? So for example, if I have مثلا 3 bits, I need to have 8 different unique combinations, صح? So I can use 1 signal element, in which case I need to have 8 levels. Okay? If I use مثلا 2 signal elements, this can drop to half, because I have 2 signal levels, and if I have مثلا if I have 3 مثلا signal levels, then 3 to the power 2 is 9. So 3 to the power 2 is 9, and I need 8, so that's fine. So I always need to have the number of bit representation less than the number of signal elements that I can generate. يعني if the number of data elements, اللي هو number of combinations that we talked about, one of these combinations cannot be represented using any signal elements, can this happen? Can this be a complete line coding scheme? No, because I have some of the combinations I cannot represent. So that does not work, right? So at least the minimum, I need to have the number of data combinations have to be equal to the number of signal element combinations that I have. This is the minimum. If I have more signal combinations, then it's better, it's good. We will see how we can use these extra signal combinations for our benefit. We can use that to enhance. We will see how. There are some ways to enhance the performance by using these extra signal combinations. We'll see how. but at least I need to have this this simple rule fulfilled all the time. The number of bit representations or bit combinations has to be less than or equal to the number of signal combinations. Okay? Any question in this part? Okay. So so in general, we have the naming convention for this category of techniques is this M, B, N, L, where M here is a number. B is always there, refers to binary, because always the data that we are talking about here is binary data. Is always binary data. So the B here refers to binary, and this stays there all the time. N is the number of bits in each group. So for example, if I take 2 bits at a time, then this is called 2B. If I take 3 bits at a time, this is 3B, and so on. Which means I take each M bits of the binary data and represent them. Okay? So the first half here, refers to the data side, or the bits, the digital bits. The second half of the naming convention refers to the signal representation, or the signal combinations. Okay? Where N refers to the number of signal elements. So N is the length of the signal pattern, or the number of signal elements. And L refers to the number of levels are used in each signal element. Okay? So again, N is the number of signal element. For each signal element, I can use 2 levels, 3 levels, 4 levels, 5 levels. زي ما أنا عايز. Okay? So M is the length of the binary pattern. B means binary, and it stays there all the time. N is the length of the signal pattern, the length or the number of signal elements. And L is the number of levels in the signal, or the number of levels in each signal element. So it's very commonly used that instead of using L as a number, they usually use what they call binary to refer to the fact that L is 2. So when I see the letter B here, this means I know على طول that the number of levels, or L, is equal to 2. If I see the letter T, which stands for ternary, this means that the number of levels in each signal element is 3. If I see Q in this letter, this means the number of levels is equal to 4. Q stands for quaternary. Okay? Or quarter. It refers to 4. Yeah. Examples, because this might sound a little bit difficult and it's getting very deep. That's fine. When we talk about examples, this becomes very easy. So, example. This technique talks about 2B, 1Q. What does that mean? Again, 2 معناها the length in each group is 2. معناها أن I'm taking each 2 bits at a time. صح? Each 2 binary bits. And then I will use one signal element. I will use one only signal element with quaternary levels, or 4 levels. ماشي؟ واضحة؟ يبقى إيه؟ I will take each 2 bits in the digital data, which is what's happening here, So, and I will then map these 2 bits into one signal element with quaternary levels, or 4 different levels. So as we can see here, we have positive 3 voltage, and we have positive 1, and we have minus 1, and we have minus 3. Okay? So we have 4 different levels and one signal element. That's why N for the signal element here is 1. Okay. It turns out that, do we have the rule fulfilled? Well, 2 to the power 2, which is the number of bits in each group, is 2. 2 to the power 2 is 4, right? And we have 4 different signal levels, right? So here, 2 to the power 2 equals to 4 to the power 1. 1 here is the number of signal elements, right? For each, I have one signal element and 4 different levels. So 4 to the power 1. So if I increase the signal elements to 2, this becomes 4 to the power 2. And I have plenty of different signal representations I can use. Okay? But here the rule is exactly fulfilled. Is fulfilled at the equal sign. Right? If it's less, we will see that this is even better. طيب. How does this scheme work? I can simply map each 2 bit combinations into one signal level, right? So I can say that 0, 0 will be positive 1 voltage, 0, 1 will be positive 3 voltage, 1, 0 will be minus 1, and 1, 1 equals minus 3. That's it. Okay? So as simple as that, I can map 1 to 1, and that's it. What is this? What is this second column used for? So let's see. Let's analyze this scheme similar to what we have done before, based on the first column only. Based on the first column only. Yani we have 1-to-1 mapping. That's it. So in that case, do I have baseline wandering? Well, if I have consecutive zeros, I will take each 2 zeros and I will map them into 1 voltage, right? So I have constant voltage, positive voltage, so baseline wandering will still be there. I have, unfortunately, if I have constant voltage above 0 and it's constant, unfortunately also I have 0 frequency and positive power, because the voltage is positive, then I have DC component. Okay? And what about the self-synchronization? Again, I have no self-synchronization. If I have consecutive zeros or consecutive ones, or hatta 0, 1, 0, 1, 0, 1, or 1, 1, 1, any of these combinations, if it exists, I will end up with constant voltage, in which case I have no self-synchronization. Okay? Then someone might argue, what is the benefit here? Why? Why do I need to do this? The main benefit, what I gained is actually bandwidth. Bravo عليك. دي الناس صح. Because R is actually doubled now. R is 2, which means 1 over R will be 1/2, multiplied by the C factor, which is 1 over 2 again. So I end up with a baud rate of N divided by 4. So the minimum bandwidth is actually is drastically reduced. So this is the advantage here. Can I enhance this a little bit? This is what this column is for. What happens is that this column tries to use certain logic to create some kind of, again, inversion in the polarity. Inversion in the polarity of the voltage. Okay? So I will use this first column if the current voltage level is positive. And I will use this column if and only if the current voltage level is negative. So let's run this example. Let's run this table on this particular example. I have here 0, 0, and assuming positive original level, which means I go to the first column. صح? Because the current level is positive. So I have to map based on the first column. When I map based on the first column, I have 0, 0 is positive 1 voltage. So I have positive 1 voltage. So the current voltage level now is positive. Then, again, I go to the same column. What is the incoming 2 bits? 1, 1. So I have to go to this column, and 1, 1 is negative 3. So I go negative 3. What is the current voltage level now? It's negative. صح? Then I have to go to the first column or the second column in that case. What is the incoming bits? It's 0, 1. So 0, 1 is minus 3. Again, minus 3. So I stay in the same voltage level. What is the current voltage level? Negative. Then again, I go here. 1, 0 is positive 1. So I will go up, and I will keep doing that. Okay? So why do I need to have these 2 columns? Why not just one? Let's see. We said that if we have only one single column and we have the same repeated bit pattern all the time, then we end up with constant voltage, right? But assuming that I have a repeated bit pattern of اللي هي let's see مثلا 1 0 1 0 1 0. Okay, this means that again sorry خليها كده أحسن. So previously we said that we will map 1 0 to minus 1 all the time. But let's see now. The first 1 0 will be minus 1, صح? What voltage level do I have? I have negative voltage. Then I have to go to which column? The second one. So if I go to the second one, I will find it positive. So I'll go positive. And then, now it's positive, then I go negative. So I eliminated the problems of constant voltage in 50% of this bit combination. So I don't have any more constant voltage if I have the same repeated pattern. And this happens for the case of 1 0 and 1 1. What about the other 2 cases? Try it at home, you will find that there's no change. Because you always keep the voltage positive and you go to the first column all the time. So the problem will not be resolved. But at least by using this polarity inversion, I was able to fix the problem in 50% of the time. فهمنا؟ يبقى I'm using the polarity of the voltage for my benefit. طبعا by using these 2 columns, the receiver can actually use the exact same 2 columns to decode. يعني there is no discrepancy. There is no problem here. The receiver has to agree with the sender that you are using 2 columns and I'm using 2 columns. If you're using 1 column, I'm using 1 column. By using this polarity inversion, we have seen that we can fix this constant voltage problem at least 50% of the time. Okay? To fix it for all combinations, we have to have some redundancy. We need to have some redundancy. By redundancy, I mean that this rule here above, this rule here, will have to be fulfilled by the less than, not by equal. Which means that we need to have some redundancy in the signal combinations. Yani we need to have some extra signal combinations in order to eliminate this problem for all the different data representations or data combinations. We need to have some redundancy, some extra signal elements. ماشي? But at least by using this polarity inversion, I was able to roughly resolve the problem 50% of the time. This, the line coding scheme is one of the most critical topics in this course, by the way. Just to draw your attention. It's one of the most difficult and most critical one. Because it goes a little bit deep. And there are so many cases and combinations and stuff which you need to be aware of. It needs many exercises in order to really be able to distinguish between the different line coding schemes and so on. Okay? So we'll continue next time for how we can use the redundancy in the signal representation for our benefit to resolve some of these issues.